On to section 11.2, which is titled Differentiation of Vector Fields. So let's just recall really quick, we know how to take derivatives of curves. Curves are indexed. Gamma is like a function of time. So curves are indexed over time, so you would just take d dt of those. Those are very straightforward. We can take gradients of vector scalar fields, gradients of scalar fields, with the gradient being precisely partial x, partial y, partial z. And now we're going to try to apply the gradient as a vector to V, which is itself a vector field of x, y, and z. Now, this by itself doesn't necessarily make sense because we're trying to multiply vectors, right? The gradient's a vector, the vector field's a vector. What does it mean to multiply those? We're going to take an aside right now and find out. So I'm heading over to the whiteboard, and I want to talk about a few things when it comes to multiplying vectors, which I think isn't talked about as often as I would like it to be. Maybe I'll put this in quotes because it's not quite clear what that means in a lot of cases. So we've probably seen this before. We have the inner product, also known as the dot product. And that's where we take vectors x1, x2, x3, dot y1, y2, y3, and this outputs a scalar, right? We gain the output x1, y1 plus x2, y2 plus x3, y3. So we output a scalar from two vectors. And this was called the inner product. And I want to specify what's going on with this word inner. Inner in the sense that it reduces dimension. So we've reduced our dimension from 3 to 1. 3 to 1 in this case. Now, as opposed to that, we actually have what's called an outer product. And this is not talked about as often as I think it should be, especially when you get into physics. A lot of physics uses this all the time. And there's not really a notation for it. We normally, right, with the inner product, we would normally write something like x as a vector dot y as a vector. With the outer product, we'll often write something like x as a vector, and we'll just concatenate it with y as a vector. So we'll just place them right next to each other. We won't put a dot in between them. But this is defined by x1, x2, x3, y1, y2, y3. Okay, so for the same reason that in an inner product, really what's happened is that's become transposed. We're going to transpose the first one here as well, which will now look like x1, x2, x3, y1, y2, y3. And now it's coming back to me that sometimes this will get defined. Sometimes this will be called the Kronecker product. And they'll use the O times, which should look like tensors if any of you have worked with tensors. Well, anyway, this gets defined by, we actually produce a matrix, x1, y1, x2, y1, x3, y1, x1, y2, x2, y2, x3, y, x3, y2, x1, y3, x2, y3, x3, y3. So that's our outer product, and if we look a little bit critically, what's going on is we're taking all combinations of x's and y's, and we're fitting those into our matrix. Okay, so we have all 1-1 combinations, 1-2 combinations, 2-1 combinations, 3-2, etc. Every single possible combination has fit into our matrix. And in particular, the way I've colored this so that you can see that each of the three colors by row or by column fixes in each row, like the y has been fixed in each row and the x varies, and then vice versa in each column the x has been fixed and the y varies. And this is indexed in the very specific manner that really it's this x has been multiplied by the entire matrix to give me the first column, or x has been multiplied by the entire vector to give me the first column. In the second case, x2 has been multiplied by the second vector to give me the second column. And in the third case, x3 on the whole vector to give me the third column. And so that's how we can think about the outer product of vectors. So outer product, since we increase dimension, and I'll put dimension in quotes, we actually gain a matrix. So we're gaining a matrix out of the multiplication of two vectors. All right, so how does this compare then? Let's jump back. Here, the whole idea was that we want to define nabla v for some vector field v. We're going to define this with an outer product. Okay, so that's going to get defined as the outer product of nabla with the vector field v. So what would that look like in particular? I'm going to jump down here. It's right here. Okay, so we're going to give this a name. We're going to call this outer product the Jacobian, and you can either define it like this, the bottom V should be capitalized there. You can either define it as the following, where we're taking nabla and acting it on V1 transpose, V2 transpose, V3 transpose, etc. Or you can recognize that in fact this is the outer product of nabla with V, right? So you can see now if I take, let's say this is partial x, partial y, partial z on the column vector v1, v2, v3, each respectively functions of x, y, and z. And what we get out of that is a matrix. Okay, that's not a dot product. It's an outer product. And so we gain a matrix. Why is this actually useful? Well, we'll talk about that. Let's move down. So it's the x. How does the x component of the vector change as we move through space in the x direction? How does the x component of the vector field change as we move through space in the y direction? How does the x component of the vector field change as we move through the z component in the y direction? I guess maybe another way of thinking about this as powerful is that Taylor series-wise, series for the vector field v, we have something like v of x, y, z is approximately v at some point, call it 0, 0, 0, so v at the origin maybe, plus the Jacobian at that point, 0, 0, 0, times the vector, and this is matrix multiplication on a vector x, y, z plus dot, dot, dot. So really the point of this is to extract some sort of Taylor series that's like our regular Taylor series before these vector fields. Okay, let's compute a Jacobian, because it doesn't mean anything if we're not computing these. So here's a nice vector field. And we're going to compute the Jacobian. So let's take nabla v. And where does that take us? Well, top left corner is just the partial x of the first component. This partial x of the first component gives me 2x. Move to the right, I gain partial y of the first component. That gives me 2y. And finally, partial z of the first component, 0. I shift down, I do partial x of the second component, 0. Partial y of the second component, 0. Partial z of the second component, 1. I move down again, partial x of the third component, 1, partial x of the, or partial y of the third component, 1, partial z of the third component, 1. All right, so this is what I'm claiming is the Jacobian. Let's scroll down and see if we've actually got it right. There we go. We've performed it correctly. So that's how we can think about computing the Jacobian. Something else that they mention about this is that if you recall from linear maps, this would have been maybe a chapter or two ago, in linear maps, the matrix, if we have a matrix with some entries, it maps some object in three-dimensional space. A matrix will basically map, let's take a cube, for example. Okay, so the matrix A maps a cube into a new space, and the cube gets shifted, right? So maybe the cube now looks like this weird looking cube in the space, and the determinant describes the change in volume that the cube experienced when it got mapped. And so the determinant of the Jacobian does the same thing, but it's doing it for an infinitesimal cube. That's what you can think about. So I'll say determinant J calculates the change in volume for an infinitesimal small cube at that point. So if we evaluate the Jacobian at the point x, y, z, and we take like an infinitesimally small cube around x, y, z, the determinant of the Jacobian says how much does that change in the image, which really you can kind of think about it as saying how do the vectors pull on the cube, right? The vectors that the vector field is putting on the cube are going to pull on it in a specific way. Moving on. Okay, so that's the Jacobian. And so it has some nice properties. Mainly, you want to think about it like this is our Taylor series property. It's the linear approximation to the vector field at a given point, the same way that we think of derivatives like that. But we have these other words called divergence and curl that I'm going to describe really quick. So we're going to jump back over to the whiteboard here, and I'm going to clear that. I'm going to do the following. So this is still multiplication of vectors. We have two other operations other than outer product at our disposal. Right, we have the dot product, and we have the cross product. These are also products on vectors. Okay, and this is where these next words, divergence and curl, arise from. So divergence is the dot product of the gradient with a vector field. And if we computed that out, we would find that it's partial v1 partial x plus partial v2 partial y plus partial v3 partial z, which would also happen to be the trace of the Jacobian, if you recall the definition of trace. But that's where we would calculate the dot product of the two, and then we have what we call the curl, which is the cross product of the two. And I'll show you the definition of the curl in a bit. So something that I want to mention about these is that, okay, so we had the Jacobian, which took me from a three-dimensional vector into really a 3x3 matrix. So I jumped up the dimension. The divergence is taking me from a three-dimensional vector to a scalar, which I can think about as a 1x1 matrix if I want to. And the curl is taking me from a three-dimensional vector to a three-dimensional vector, which I can think about as m 3x1. Okay, so these are really the three operations we have on vector fields. And we've talked about the Jacobian, and now I'm going to talk about why maybe the divergence and the curl are actually important. So let's jump back to the page and scroll down a bit. Okay, so here it says sources, sinks, and divergence fields. So I want to comment that here we see now the divergence just as I described it on the previous page. And why do we call it divergence? Well, what does it mean in English? To diverge is to point and travel away from each other. I think we all know what diverge means in English. Well, let's think about a vector field. Suppose I have two vectors here, and they point and travel away from each other as the following. The divergence doesn't calculate the angle, but the divergence calculates the total amount this occurs at the point x, y, z. That's what we can think about, right? So in fact, we have vectors traveling in every possible direction from, and this is really neighboring points, right? We should put these at two neighboring points infinitesimally close to each other. But divergence is saying, okay, given 2 points that are infinitesimally close to each other, how much do they spread apart? How much are they kind of pointing? It's an infinitesimal amount that they're pointing in different directions as well, but like, what is that spreading action which is occurring? That's what divergence is calculating for me. So let's scroll down and let's look at a nice little vector field. So first of all, here's a vector field, x, y, z. I'm going to make it really easy. We can calculate the divergence. All we're going to do is calculate the partial derivative on x plus the partial derivative, with respect to x, plus the partial derivative on y with respect to y, plus the partial derivative of z with respect to z. We end up with 1 plus 1 plus 1 equals 3, right? So this is giving me a positive divergence everywhere. What do we think a vector field with a positive divergence everywhere should look like? Well, it means that vectors should always be spreading out from each other. Right, positive divergence, vectors spread from each other. What would that look like as a vector field? Well, I'll scroll down, and there's a vector field with a constant divergence of 3. Basically, what you can say is that the spread of any two vectors is linear, because 3 is a constant number, and the derivative calculates linearity. So the spread of vectors is constant, and they're constantly spreading by an amount of 3 from any given point. We have a product rule for the divergence as well, just like we would see it with the Jacobian. This is very standard. All of these are operations we're talking about are called derivations, and a derivation needs to satisfy the product rule. So that's why we have a product rule there. Now we're going to push over to curl. You've noticed that it decided to start this as rotation fields, but really this section should be called curl. And we give it the name. Why should we talk about what the name of the curl is? In English, I know I sometimes capitalize and sometimes don't. I think it should always be capitalized. In English, curl means the rotation an object has when traveled through. And so we're going to get the same sort of behavior here. We're going to say curl is the rotation. We're calculating the rotation that the vector field has when you travel through some specific point. Now, why is that calculated by the cross product? Well, I'll show you really quick. So the cross product can take this very specific form. I promised I would show you the form earlier. So if you recall your cross product from the earlier chapters in this book, if I take x1, x2, x3, and I cross it with y1, y2, y3, by definition that gives me, let's see, it's x2, y3 minus x3, y2, and then we have negative x1, y3 plus x3, y1. And then we have positive x1, y2 minus x2, y1. Okay, so that's the definition of the cross product. And what a cross product does is it calculates the normal to the vectors x, y plane. So the vectors x, y form a plane, and we can calculate the normal to that plane with the cross product. So that's a definition of the curl. But why does it describe the rotation of a vector field? Well, let's just scroll down a little bit. So here's a nice little vector field for us, and we can calculate the cross product of this. Let's actually go through that calculation really quick. So what I'm looking for is partial y on v3. Okay, so partial y on that z there is going to give me 0, minus partial z on v2, which is partial z there, is going to give me 0. Then I have partial z on v1 is also going to give me 0, minus partial x on v3 is also going to give me 0. Finally, we better see something that shows up. Partial x on v2 gives me 1. Partial y on v1 gives me minus -1. I end up with 0, 0, 2. So this has a non-trivial curl, but what does this vector mean? What does the vector 0, 0, 2 mean? How does that correspond to maybe some rotational aspects here? Oops. So we'll scroll down and let's look at our vector field. So there's the vector field, and we can see it's definitely rotational. But what does that curl vector really mean? Call the curl. Curl of v was this vector 0, 0, 2. And that vector is precisely this one. Now, why does this field, why should it behave in a way that is calculated about rotation? Well, this is where we have to remember our right-hand rule from physics. If you haven't taken physics, you'll definitely encounter it eventually, which basically says if we want to calculate the vector of angular momentum, we are going to place our fingers on our right hand, curling in the direction of a vector field or of angular motion, and then the thumb on our right hand is going to point in the direction of the vector, which defines the angular motion. So that's why this field has the curl can compute the angular motion of the field or the rotation of the field as 0, 0, 2, because if we looked at this, and especially if we looked from above at this vector field, we would see it rotating in a counterclockwise direction from above. And so that should say that our curl vector should point vertically. And so that's what this calculates for us. As the magnitude increases, it says that we're spinning faster and faster. Okay, so finally, there's this very interesting idea that we can break a vector field into a swirling part, which kind of describes this is the x and the y parts here describe the swirling motion, as well as the divergence part, which z kind of describes how far the vector field was spreading as we moved up and down in the z direction. So I'll scroll back up there. So you'll notice that as we move up and down in the z direction, right up here, it's kind of spreading, upwards. That's a divergence of z, and this is spreading downwards. That's a divergence of minus z, and right in the middle, it's spreading nowhere. That's a divergence of 0. So we have a divergence part that's really like the vector 0, 0, z, and then the rotational aspect is really the vector minus y and x. And there's really a decomposition that you can produce on vectors because of that. I'm just going to mention that briefly. That's called the Helmholtz decomposition, and it's something that physics really cares about, but we're not going to worry too much about it in this course. Anyway, that's all I have. Thanks for watching.